Okay, so let's review a little bit about the class material that we covered last time. So the last theorem that we had over here is this. This is like a Henkel matrix. The inverse of the Henkel matrix can be written in this way. And yeah, after the talk, Dr. Minho Song pointed out to me that this can be seen as LDU type decomposition, and I think that's interesting. So let me tell you a little bit about that. So here's the review. So we have this. But let me just okay, so application of this is that that means mu, let me rewrite this in this way, I plus j, so ij from 0 to n. And if you take the inverse of this, and that its entry will be exactly this, but that can be written in this way. So nu ij I comma j from 0 to n, and I take the transpose of this and diagonal matrix. This means that the diagonal entries are these: lambda 1 inverse, lambda n inverse, and nu ij from 0 to n. Because if you think about the r comma s entry of this, you know, you multiply this and this and this, because this is a diagonal matrix, you get this. Okay. So here we know that this inverse is this. We know that these mixed moment and coefficients are inverses of each other. So if you take the inverse, then we get, take the inverse both sides, then we get this. By the way, this is lower triangular, upper triangular, lower triangular, diagonal, lower triangular. So this is UDL decomposition, right? So triangular matrices and diagonal. And if you take the inverse both sides, then you get this matrix identity, ij from 0 to n, and this is this inverse of this inverse of this, but that's exactly this. So it's a mu I comma j ij from 0 to n. The inverse of the diagonal matrix, you just take the inverse of the diagonal entries, lambda n, and here you take the transpose and inverse, so it's mu ij transpose, like this. Okay. But now let's look at the r comma s entry. So then the r comma s entry can be computed by multiplying these three matrices, and that's exactly like this: k from 0 to n, mu rk. If you take r comma k entry here, you have to take k here, so k comma s. So here you multiply lambda 1 dot 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 lambda k for the entry from the diagonal matrix, and then you multiply mu k comma r from here, but it's a transpose, so k comma s, so s comma k, like this. Okay, but we can rewrite this because we know that this is mu r comma 0 comma k lambda 1 lambda k mu s comma 0 comma k. We just write it. That is the definition. But this is in fact, if you think about this, it goes from the length is s, height starting height 0, ending height k. It goes like this. But if you multiply this, then actually you can change the starting and ending height. This is in fact, you can see this must be equal to k comma 0. Because if you start from k and end it here, then you get up steps become down steps. So they contribute weights there. So, but now if you think about it, what does that mean? So everything here is like, this part here is like, you have r plus s. Starting and ending height are both 0. But then of course, if you just consider r and s, this can be anything. This k can be anything. And that's why this is exactly the path from here to k, 0 to k, the length s from k to 0. So this really explains the kind of trivial identity if you consider the matrix, the Machkin path. So they are all equivalent to this formula that we proved, which is more complicated. But if you look at this, this is more natural. But they are all equivalent in this sense. And this is the LDU decomposition of the Henkel matrix. Okay, so that's what I wanted to say about the last lecture. Now we're gonna move on to the next chapter. So chapter 8. This is about continued fractions. So continued fractions are kind of classical objects in mathematics, and they are closely related to orthogonal polynomials. And in fact, it's written in the literature that orthogonal polynomials arise when people study, in order to study continued fractions. They're very closely related. So we will see their connections in this chapter. But first, we need to study the basics of continuous fractions. What are they? Fractions. Okay, what are they? So let me begin with an interesting example. Probably many of you have seen a problem like this. I think it goes like that. What is this? Have you seen a problem like this? I think I've seen this when I was, high school or even middle school, and I couldn't solve it at the time. But I found a proof, and proof was kind of brilliant, because we don't know this. Let's say this is x, and we want to find x. But if you look at this is exactly the same thing as itself. It's like a fractal structure. So if this is x, this part is exactly the same. So x, we must have 1 plus x equals x, right? But now we can just solve this equation. So it is x squared plus x minus 1 equals 0. So x equals just a quadratic equation. So 1 plus 4. So square root of 5, plus or minus, square root of 5 minus 1. But we know that it cannot be minus because everything is positive, so it should be positive. So we choose a plus sign here. So the answer is square root of 5 minus 1 over 2. It's like a golden ratio. So are you satisfied with this solution? Or do you understand this solution? Now, if you understood this solution, you're a good student. But if you don't understand anything about this solution, then you probably are a good mathematician. Let me tell you, because the proof, the answer is correct, but the solution needs more rigorous arguments there. Just because, let me just tell you another example. Let's do the same thing with this. Same thing. Obviously, we can apply the same, try the same thing, x. Not exactly x, but 3 minus 3, and then if you look at this is exactly x. So 1 over 1 minus 3x equals x. Now let's just solve it. But if you multiply, then move 3x squared minus x plus 1 equals 0. So x equals 1 plus or minus square root 1 minus 4, 3, so it's 12. But this is weird because, you know, this is complex number, not a real number. But this must be real. Everything is real, so why should we get a complex number? So there is something wrong in this argument, right? That means, you know, there is something, but it works here, but why it doesn't work here? So there is something that we need to check more rigorously. But first question that you should ask here is, what does this mean? What does this even mean? Does it even something precise? Do we have a precise definition? Or because I just this is just a kind, as a if you are a mathematician, you should think of this as just a picture, drawing. It doesn't mean anything except just a list of object. It's like a sequence of ones. That's all that means, because we didn't really define anything precisely. But if you can define things precisely, then this will make sense. So the definition looks like this. So continued fraction, there might be different types of continued fractions, but we will look at this kind of continued fraction. It's just an expression of the form. Just like this, beta 0 plus alpha 0, alpha, let's begin with alpha index 1, beta 1 plus alpha 2, beta 2 plus alpha 3, So you clearly see the pattern here. For some sequences, beta n and alpha n. Okay. So in other words, continued fraction is just a pair of sequences, just displayed in this way. It doesn't mean anything so far, just a pair of sequences. Like the formal power series, you know. But we will talk about, but we want to somehow say that this is equal to something. So to do that, we need to define this. So the nth convergent of this continued fraction is the same thing, except we finish at the level n, say. You go like this, and at the end you get something like alpha n over beta n. Okay? So we're gonna write this as Cn, convergent. So for example, C0 equals beta 0, C1 equals beta 0 plus alpha 1 over beta 1, C2 equals beta 0 plus alpha 1, beta 1 plus alpha 2, beta 2, like this. Okay? So now everything is concrete. It's a rational function in the numbers alphas and betas. So everything is fine. So when we write this, we write this continued fraction equals L to mean L is really the limit of this conversion and approaches infinity. So that means this conversion must converge to something, and that is L. That's what this notation means. So in this, if we go back here, then we can consider the conversion here. One, like this is nothing, so 1, and then 1 over 1 plus 1, 1 over 1 plus something like that. Then you consider this sequence, and now everyone knows what convergence of a sequence means. So in that sense, the limit of that sequence is x. And then, so when you talk about the limit, you have to really check whether the limit exists. So in this case, you can show that the limit exists. And if the limit exists, this argument now works. So it has to satisfy this. So if the limit exists, it must be this, nothing else. But here, the limit cannot exist, because if the limit exists, it must be this, but obviously it cannot be. A sequence of real numbers cannot converge to a complex number, non-real complex number. So the important thing that I want to say here is that we have to check whether the limit exists or not, and that's what continued fraction means. And now we will move on to the next section. It's about continued fraction combinatorial theory due to Flageolet. So Flageolet wrote a paper in 1980 about this, and it's quite influential. Combinatorial theory of continued fractions. Let's talk about this. And we're gonna use this notation. So this is boldface B is a sequence of B's, like our recurrence coefficient. Lambda boldface lambda is our sequence lambda. From now on, I'm gonna use this notation and define this mu as usual, using only Motzkin path, just combinatorially. So pi Motzkin path of length n from level 0 to level 0, and the weight in the usual sense, but I'm gonna just to emphasize that we have b's and lambdas, I'm gonna emphasize b and lambda there, because we will change b and lambda in this chapter. In the usual weight, so horizontal has weight di, lambda, down step has lambda I, the usual weight. And finally, let's define this generating function for all Motzkin path with weight b lambda. So for all n, mu n b comma lambda, x to the n. So it's basically the generating function for the moments of the orthogonal polynomial. Now we want to investigate this generating function, and we will use this observation, the observation that we actually saw before. So let's say pi is a Motzkin path. From now on, I'm gonna say in this chapter section at least, every Motzkin path is a path in this set, right? Level 0 to level 0, always, okay? Then we have three possibilities. There are three cases. Case 1, pi is not empty set. It's not nothing, just a single dot from 0 to 0, okay? And second, if it's not the empty path, then there must be a step. So the first step could be horizontal. So pi could be horizontal, and then a Mochkin path, something else, something else, like this and this. Pi prime is over here. Or the first step is an up step, so up, and then we have some Mochkin path, and then down, and then pi prime. So up, so pi, this means up, something down, and something like this. So the pi prime, pi double prime, both Mochkin path. We always have exactly one of these three situations. Okay, and what happens in the first case? In the first case, what is the weight of pi? Let me write it this way: b lambda, of course, as 1. Product of nothing is we define it to be 1. What is the weight of pi comparing with the weight of pi prime? We have an extra step, but this is the same. This is the exact same weight will contribute to pi. So the weight of this is b0. So it's b0, and the weight of pi prime, b and lambda. Okay. And 3. This is the interesting case. Up step doesn't have any weight. The the down step here has weight lambda 1 because the height is 1. And pi double prime, the same weight will contribute to pi. So we have lambda 1 and the last pi double prime, the same weight like this. Okay, but this, I mean, pi prime, I mean, it's a path from 0. This, I consider this as a Mochkin path with this 0 level. Okay? Then we cannot simply put this. We cannot simply say this because the weight is shifted. So this weight here, if you consider in this weight, this will contribute lambda 2. Lambda 1. But it should really be lambda 2 because the height is shifted by 1 above. So to solve this, to resolve this situation, I'm going to define this notation, delta. It's an operator, delta, which just shifts the sequence by 1. Or, yeah, so where this delta B is the sequence starts from P1 like this. The lambda, if you apply delta, you just shift lambdas by 1 like this. Then it's going to be right. So originally, this will contribute to lambda 1. But lambda 1 is lambda 2, so it will be lambda 2. So everything is fine. So we have this situation. Okay? So if you combine this, f of x, b comma lambda, so this is the generating function for all path, Mochkin path, weight of pi. But we know there are 3 cases. First case, the weight is 1. The second case, the weight is b0 and pi prime. And third case, lambda 1, pi prime. But here we have to shift the weight and double prime. And this is the same. Okay? But if you look at this, this is B0, and this part is exactly F. Right? This is just F. This is also F.
I think we need extra X there.
Oh, yeah, that's right. Yeah, thank you. X. Because, yeah, we have to consider this as well. Yeah. And also here, X squared, right? Thank you. So here is x. And plus lambda 1 x squared fx. But we just, it's exactly the same thing except we shift the sequences like this. But the second one is the exact same, like this. Now we have a functional equation for this sequence, or the generating function. So we can move this to the other side, and then combine them and divide the factor. Then we get an identity like this, equals 1 over 1 minus b0x minus lambda 1 x squared f x delta b delta lambda. Okay, because if you move these the factors, so we get this and this appearing here. All right, now this and this, they are exactly the same except we just shift this. So we can apply again to this the same formula again. Then this will give us 1 minus b0x lambda 1 x squared. So it's going to be 1 over, so 1 minus b0, but b is shifted, so b1x lambda 1, but lambda is shifted, so lambda 2 x squared, and f x delta shifted twice, like this. Okay? You can keep doing this over and over. So if you do this over and over, then we will do this infinitely many times, then you will get something like this. 1 over 1 minus b0x minus lambda 1 x squared over 1 minus b1x minus lambda 2x squared over 1 minus p2x minus lambda 3x squared over, and then like this. But is it really true? To really check this rigorously, we have to really look at the convergent. So let's see. So actually it's true, and we will find a rigorous proof of this. But to do that, we need to define the convergence in formal power series. So let me define a convergence of formal power series. Suppose that this sequence of formal power series in X, and we write a limit. What does a limit of a formal power series sequence mean? What does this mean? This means for every m there exists n. It's like epsilon delta argument, such that for all n x to the m f n x equals x to the m f x. But here this means the coefficient of x to the m in fx. Okay? What does that mean? So if you're comfortable with epsilon delta argument, this should be understandable. So what does that mean? So just fix m. Then you look at the coefficient of x to the m here. And you look at the coefficient of x to the m. Of course, they may be different, but if n is big enough, eventually the coefficient becomes exactly this. I'm not saying that the coefficient converges to the coefficient of this. It just becomes it's exactly that coefficient. Okay? At some point, It could be different, but at some point, after some point, it's constant, and that is exactly this. That's what a formal convergence means in the formal power series sense. Okay. Yeah, maybe it might be good to have an example, but let's see what kind of example can we define. Okay, let's see. 1 plus, just a simple example, x squared like this. And I'm going to define fn 1 plus x to the n. The polynomial is a formal power series also, right? So in this case, does this converge to f? And the answer is yes. Because for any, just pick any m, and just look at the coefficient of x to the m. If n is big enough, this coefficient of this will be always 1, right? If n is greater than m. So at some point after m, then coefficient becomes all 1, which is 1, the coefficient of this. So it converges to this. Okay? This example is something like that. So in this sense, we need to, we can consider the convergent of this. So convergent means you truncate the continued fraction so that it's a finite fraction. So we're gonna define this mu n less than or equal to k b lambda is the generating function for all Matchkin path. This notation means that this means you can imagine all Matchkin path with height less than k. So something like that. It may touch and even go horizontal in this. So height, maximum height is less than k. Okay? And you only consider those here. That's the definition of this notation. Okay? Pretty simple. If k is infinity, then you can just ignore this. That's the usual moment. Okay? And the theorem is, this is exactly the nth convergent or kth convergent. For any k, of course integer, we have the generating function for all Matchkin path of bounded height x to the n equals 1 over 1 minus b0x lambda 1 x squared 1 minus b1x minus lambda 2x squared dot dot dot, and the last one is this. You go up to this. Okay. This is so how can we prove this? Proof is induction on k. So k equals 0. What happens? What is this? The left-hand side. The height is 0. So only one Matchkin path for every length n. They all use horizontal steps of height 0, so you have only b0 there. b0 to the n, x to the n, but this is a geometric series, 1 minus b0, x. That's exactly the convergent here, when k equals 0, okay? So this is done, but what about the next step? So suppose it's true for k, and consider the k plus 1 case. Let's say k minus 1, true for k minus 1, and then we're going to consider k. Okay, for the case k, we consider Matchkin path. The decomposition of pi. Every Matchkin path we have decomposition. 3 cases: empty, horizontal, or up at the beginning. So pi is either empty or horizontal or up. This. So that means generating function for let's use this notation. Yeah, just for, because we cannot really write all the time. It's the generating function for this. Okay, the usual way. So using this decomposition, we see that if it has no steps, then there's 1. If a horizontal step, then we get, this is exactly what we had before. The same argument, yeah. Plus lambda 1 x squared f. But here, if the maximum height is k, what is the maximum height of this? K minus 1. So we have to change this into k minus 1. And then we shift in the usual way. Times, I think maybe I can just use some more space. K, that's the same. Okay. Now we do the usual thing that you move this other side and then divide. Then we get fk equals 1 over 1 minus b0 lambda x lambda 1 x squared f k minus 1 x delta b delta lambda. But see, this is k minus 1, so we can apply the induction hypothesis. So they are shifted, so we write this in this form, but they're all shifted, so it starts from 1, 2, 2, 3, dot, dot, dot. That's exactly matches with this b0, b1, b2, lambda 1, lambda 2, dot, dot, dot. So this actually shows that true for k. So by induction, we are done. So proof is not that difficult if you know what to do. And now we can finally give a rigorous proof of that continued fraction formula. X to the n equals 1 over 1 minus b0 x minus lambda 1 x squared over 1 minus b1 x minus, let's just write it this way. Okay? So why is this true? What does this mean? The meaning is nth conversion. We look at kth conversion, say fk. And then we have to show that this limit is equal to this. That's what this formula means, identity. So by the theorem, we already know that kth convergent is fk is a generating function for n let me omit b and lambda because we don't need to change them. So we need to show this. K. Is this f? Where I'm going to write this f. This is what we want to know. But what does this mean? This means eventually this mu. This means the coefficient of n here. Is this equal to this? If k is so for fixed k, for fixed n, let me make it more precise. For any fixed n, this is true if k is big enough. Is that true? Yeah, how can you make k big enough? What is big enough here? Yeah, if you don't want to make a precise or low, you don't have to choose the lowest one. So you can just, okay, let's say n. If k is n, then this is equal to this. Because obviously, this is always greater than or equal to this because we have some restrictions here. But if the height is like n here, you have only n steps. You have to start from here and end here. You cannot really reach. Actually, n over 2 is enough. So if k is big enough, like namely n over 2, then they are always equal. That means this is true. So that's why this is true. So that's the proof, basically. Now let's move on to the next section then. Now we have, we can see the connection between continued fractions and orthogonal polynomials. Of course, we have seen connection between continued fractions and the generating function for moments of orthogonal polynomials. So you can say that kind of gives a connection between continued fractions and orthogonal polynomials. But here we will see direct connection, this and just polynomials themselves without using moments. So again, we need to introduce this notation. Before we only used p and x, but we're gonna specify b, the sequences b's and lambdas. B, the monic OPS, such that they satisfy this usual recurrence. Yeah, I'm gonna omit b and lambda. Yeah, if the meaning is clear, I'm gonna sometimes omit this. Okay. And also we write delta p and x b lambda. That means we just shift b and lambda by 1. This is the same just notation. Okay. And we need to define one more. The inverted polynomial, which I write as p n star x b lambda, is you just, as the name suggests, you just replace x by x inverse. But of course, this is not a polynomial. But if you multiply x to the n, it's now a polynomial. So this is the definition of the inverted polynomial, okay? And now we have this. What is the recurrence for the inverted polynomial? you replace x by x inverse, like this. Then you multiply x to the n plus 1, both sides. Then this becomes this with n plus 1. And here, this changes into just a simple computation. X becomes 1, but Bn, we have x attached. Again, I'm omitting b and lambda, but they should really be there. Okay? The inverted polynomial satisfy this three-term recurrence. Slightly different because the location of x is a bit different, but quite similar. So remember, this was the nth or k conversion of the continued fraction, and in fact we can express this using inverted polynomials in a very simple way. So our goal here is to prove this theorem. The generating function for this bounded Matchkin path, b and lambda, is equal to, maybe I'm gonna use this simple so it's just ratio of two inverted polynomials with index shifted by 1 and then this shifted like this. So very simple formula. Yeah, there are several proofs. In fact, we can prove this combinatorially because we know a combinatorial meaning, and because of this simple recurrence, we can express this as basically a generating function for Fabard tilings with a slight modification of the weights. So if you multiply this over here, you have a pair of Matchkin path, bounded Matchkin path, and Fabard tiling, and after some cancellation, you will only get some Fabard tiling left over. That's possible. We have done something similar to this, but we are not. But we will prove this in a different way, which is I think quite interesting. That's simple, and this we will use what's called technique, continued fraction technique, due to mathematician John Wallis. Yeah, he was born like more than 400 years ago, but we can still, his technique is still impressive, so we're gonna use it. To do that, let me define some notation. So we have fixed sequences. The alpha sequence goes from 1, beta sequence goes from 0. We have two fixed sequences, and Cn is the convergent of the continued fraction that we saw before. Like nth convergent of the continued fraction. Okay? So our goal is, so you know, these are basically this with some alpha beta specialized. Our goal is to express this as a rational function in x. Okay? So, but this is always possible because this is a rational function after all. So our goal is, can you write this as a ratio of two polynomials? How can we find the a_n and b_n? That's the idea. But you know, for instance, C0 is beta 0, so we can say, okay, this is A0, maybe I can, beta 0 over 1, so this is A0, this is B0, And C1, what is C1? Beta 0 plus alpha 1 over beta 1. So beta 1 over beta 1, beta 0 plus alpha 1. So we say, okay, this is our alpha 1 over beta 1. We can keep doing this. But of course, it will be complicated. But the lemma here is Early's method is that we can find a solution to this. We can find an explicit solution to this. We can find AN and BN, namely. So let's say A0 equals beta 0, B0 equals 1, and maybe the previous one is 1, 0, like this. Define this, and then we're gonna define AN recursively using this recursion. Actually, A and B have exact same recursion. Only the initial conditions are different. For, of course, n greater than or equal to 1. So we define this sequence, capital A, capital B. Then, yeah, AN over BN is CN. This is the theorem. You know, a theorem like this is something that's difficult to find but easy to prove. You know what to do. If you know the exact formula, then proof is kind of straightforward. But in this case, we need a little bit of thought. Yeah. Again, we're going to use induction, proof. Induction on n. N equals 0, true. See, this B0 over 1. So this is true. True. We just check it. And suppose that it's true. Yeah. And also let's check one more. Also true. We checked. Yeah, we can check as many initial conditions as we want. Just let's check n equals 1 up. And suppose it's true. It's true for n, and now we're gonna consider n plus 1 case. Okay. And to consider the n plus 1 case, I'm gonna look at this. Yeah, I'm gonna use the next slide. We look at n plus 1 case. So it's n plus 1. So this is like, let me use just one more. Like, it looks like this. We have one more fraction step. Okay. But I'm gonna rewrite in this way. Maybe I'm gonna use the next line. I'm gonna just rewrite this by multiplying beta and both numerator denominator. So this part, if you look at this, it's gonna be alpha n, beta n plus 1, beta n plus 1 plus alpha n plus 1. Okay, but you see, this is exactly Cn, except alpha n, beta n are replaced by these two. So we can use the induction hypothesis here. So Cn plus 1 is An, Bn, but of course not exactly. We have some modification where An star is an with alpha n replaced by alpha n beta n plus 1, and bn star is exactly bn with beta n replaced by beta n plus 1, alpha n plus 1. That's by induction hypothesis. Now we're gonna compute. So we need to show that this, what happens here. Okay, let's see. But because this is alpha, now is alpha star with beta n, alpha n modified also here, we modify this using the substitutions there. Then we get a formula like this. Let's just look at alpha, an stuff only, because bn has exact same recurrence, so it's enough to check this. No, I did nothing but replacing this by this and this. Okay. Now let's look at them. You see, this and this we can combine. Beta n plus 1 and beta n a n minus 1, alpha n a n minus 2. And the other one, alpha n plus 1, a n minus 1. But this is exactly this. So this an. But what is this? This is an plus 1 by definition. The definition of an sequence is this. So this is equal to this, and the same way, bn star is bn plus 1. That means cn plus 1 is an, because we can just, these two are just this. So it works. That's the proof. Quite simple, right? Now we have this lemma. Proof is almost immediate. Now, but let me copy this. I think we have to use this as well. I think I need to copy this. So proof of theorem. But let me maybe I can just make it a little small. So what is the theorem? What is the theorem? Theorem is this. Proof of the theorem, which is written over here, and then just a notation. And we need one more, the recurrence. Let me put everything here. Now we just combine everything that we know, then we get the proof. All right. Use the lemma with, because see, by the way, this is not exactly of this form, because it's something plus something. But if you think about it, this is exactly that form. So we will instead consider the denominator only. All right? So lemma with, so these are betas, these are alphas. They're exactly in that form. So beta 0 equals bi 1 minus bix alpha I equals lambda I x squared. Then AK, let me use that notation in that lemma. BK equals exactly this. Yeah, I think I can just copy this. Because that's what the lemma says. This is the convergent of this. Beta, 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 alpha, alpha, alpha. But what is A and B? AK, this is 1, 0 equals 1 minus B0x. And the recurrence is AN equals 1 minus B0x, because this is beta, AN minus 1, lambda n x squared, AN minus 2. I think I made a mistake here. It must be minus. Yeah, this is minus. This is minus. Okay? Yeah. But compare with this and this. Oh, this is n. This and this is exactly the same, except this is only shifted by 1. The index n is shifted by 1. So if you say this is an, then this is an minus 1, an minus 2, so they are the same. And the initial condition, this is P1 star, this is P0 star, so exactly the same. So that means an is Pn plus 1 star x, let's say. And same way, Bn, if you compute this, yeah, maybe I can just write that down. Bn satisfies this. Bn equals 1 minus Bn x, Bn minus 1 minus lambda n. Same recurrence, but only the initial conditions are different. So B minus 1 equals 0, B1 equals 1. So this looks like a Pn, but if you write this n minus 1, n minus 2, then this must be shifted, minus 1, minus 1. But because this is n, that means here Bn is exactly Pn star, but you have to shift this by delta, by 1. And that's it. That's the proof. That means the convergent, this is a K convergent. We know that this is AK over BK. But what is AK? Oh, sorry. Yeah, this is right, but yeah, let me write it. But we are looking at the inverse of the power series, right? So now we have to inverse, take the inverse of this to get this. That's exactly the formula that we have over there. So that's the proof. Okay. And in fact, we can do more than this. So see here. This is a generating function for bounded Matchkin path. Starting height 0, ending height 0. But we can also consider NRS for fixed R and S. Then this must be changed, of course, but not that much. We have some extra factors here, and we will prove this in the next class. So I will stop here. Thank you for your attention.